Welcome everybody to my talk on the topic cloud-based early warning system for algae monitoring in surface water. At first I will give a short introduction, we'll talk a bit about the sensors, talk about the cloud-based early warning system itself and present the current status of the project and show some results and give a short summary and outlook at the end. But first, analytics meets digitalization. What does that mean? So it means to me we have some kind of cloud-based data management system that we can use, which would be some kind of virtual working space, and that we need some kind of data warehousing to store the data. We need data processing to which would be some kind of algorithm to process the data in real time. And we need some application that it will give access to the user. And it is, for example, to read out and visualize the informations. This is a cloud-based monitoring system or management system is a powerful tool. But without data, we can't do anything with this tool. So it's important to get as much data as possible. And how can we collect the data? Of course, the easiest way is to use simple sensors. When we want to measure parameters, for example, there's the usual parameters that are always measured, like temperature, turbidity, conductivity, pH, and so on. There are, for most all of them, there are simple sensors like pH sensor that is in almost every lab. We have sensors for dissolved oxygen, so we can make use of this principle that the dissolved oxygen quenches the intensity of and lifetime of luminescence, and so we have a luminescence dye on the sensor tip, which gets we can shine with the light on this chemiluminescence dye, and the time of the luminescence gets measured. We have sons for turbidity. There's a simple method to measure it, and with the turbidity value we can calculate the total suspended solids. We have the sensors for temperature and conductivity. Usually they are combined in one sensor because the conductivity is highly temperature dependent. And with the conductivity we can calculate the total dissolved solids. If we go to the nitrate, here this device is the TRITON water sensor system to measure the nitrate in the water. It is a device from the A.U.G Signals company in Canada. It is a flow-through UV-VIS spectrometer, and with a kind of light source we have a spectrometer, and there is a kind of flow-through cell. So here this blue is the optical fibers, and here's the path length of the light, and we can have a sample inlet here on the bottom, sample outlet, and so we can measure online real time and give and record the UV-VIS spectrometer from 200 to 850 nanometers. How to calculate to the nitrate concentration, I will talk about this later in the presentation. Now I want to continue with some kind of with biosensors that are also good tools for monitoring. Okay, they are more complex, they are complicated to miniaturize. That is some point we need to still work on it. But they are very selective. They use receptors like antibodies to immobilize, that are immobilized on the sensor surface, and it's able to quantify or make quantitative analysis of micropollutants like drug residues, pesticides, microorganisms, or viruses. The device I use is the microarray chip reader. This device here, with that we can conduct flow-based chemiluminescence microarray immunoassays. The immunoassay will take place here on this microarray, which is composed of a polycarbonate ground plate with two holes, the inlet and outlet to the flow cell. In the middle there is a double-sided adhesive foil with the shape of the flow cell, and on top there's the glass slide with the immobilized analytes. The immunoassay I use is a, let's say, indirect competitive flow-through microarray immunoassay. It can be divided into 5 parts. First would be the pre-incubation of the sample with the primary antibodies, then binding of the still unbound primary antibodies to the immobilized analytes. Then there is the binding of a detection antibody and chemiluminescence reaction with image acquisition, and the last step would be a regeneration, so that more than one measurements can be conducted on a microarray. The microarray chip reader, it's provides rapid and fully automated analysis. It's possible to multiplex, so it's possible, for example, to measure different toxins like saxitoxin, anatoxin A, or microcystin. It will give quantitative and qualitative analysis at the same time. And for example, for microcystin LR, we have detection limit in the range of 3.4 microgram per liter. The working range is between 5 to 36 microgram per liter. And for saxitoxin, for example, it would be 2.3 microgram per liter with a working range from 2 to 37 microgram. Well, with these kind of sensors, physical, chemical, and biosensors, it is possible to set up a cloud-based early warning system for algae monitoring in surface water. This project is done with the project partners, the A.U.G Signals in Canada and the Hydroisotop in Schweitenkirchen. But why algae blooms? Why is it necessary to measure these? Well, algae blooms are favored by anthropogenic changes such as eutrophication of water bodies or global warming. Higher water temperatures and the overfertilization will lead to excessive production of the Cyanobacteria, and they usually produce toxins like the saxitoxin, anatoxin A, and so on, which is a risk for the, for example, the drinking water production, recreation, or agriculture. And an early warning system could provide real-time local information about the condition of surface water bodies, indicating potential algae blooms. Well, what happens while the algae bloom? There are changes in the water parameters, like turbidity is increasing because there are algae growing in the water. The pH is rising. Increase of pH is related to the consumption of the dissolved carbon dioxide by the algae. The dissolved oxygen decreases. Toxin concentration, of course, it rises, and there are also selene and sulfur organic compounds that can be measured when there are cyanobacteria present, which can be measured via, let's say, classical analytics like isotope analysis, which would be part from the hydroisotope. The cyanobacteria itself, they are secondary metabolites produced by cyanobacteria. They are mainly intracellular and released into the waters free toxins after the cell death and their decomposition. The toxins are classified by the basis of the mode of action in vertebrates. So there are, for example, the hepatotoxins that damage the liver, like microcystin LR. It leads to non-reversible liver damage. There are neurotoxins that they are destructive to the nerve tissue, like the saxitoxin, which is also known as the shellfish poison. And they have paralytic effects and lead to death by respiration paralysis. Also, the anatoxin A is a neurotoxin called the very fast death factor, because if there's a poison, death will occur very fast, within minutes or at least under 1 hour, and because it leads to paralysis and death by apnea. And so to monitor the cloud-based early warning system, to develop the cloud-based early warning system for algae monitoring in surface water, for this cloud-based data management platform, we have the sensor data. They come from the TRITON water sensor system with a multi-parameter sonde and the nitrate data from the TRITON. It is important to have other water quality data like the level of water flow, if there are environmental influences like heavy rainstorms or drying periods. And we have our, let's say, control instances like the from Hydroisotop, the measuring the selenium and sulfur organic compounds, and here from TU Munich we measure the concentration of the toxins. Before I show the some data I collected, the sampling site is near to Garching by Munich. It is at the campus of Technical University in the Wiesecker, and it looks like this. Here we have, this here is the Coexo 2 from YSI. It is a multi-parameter sonde which can host up to 7 different sondes inside. And a measuring day would look like immerging the sonde into the water for at least 6 to 7 hours and continually measure the water parameters. Every 10 minutes the device will take a data point and save it on this device, and later on, if we bring it back to the lab, the data can be uploaded in the system and get uploaded to the cloud or whatever. Well, it is also every hour there's a water sample collected to bring it back to the lab and analyze the water parameter with some reference methods, and also to measure the nitrate concentration with the TRITON system. The water data from the multi-parameter sondes looks like this. Straightforward. This is a daily water background change from Wiesecker in Germany from the 8th of March 22. Here the data points without a line belong to the left y-axis, and the data points that are connected with lines belong to the right y-axis. And one can see the water parameters did not change in the measuring period from 9 a.m. to 2 p.m. Well, there was no raining event or something that would change the water parameter. If we go to the, let's say, nitrate concentration, it is a bit more complicated to calculate the data. This, for example, is an absorption spectrum from deionized water spiked with nitrate samples with concentrations between 0.1 and 25 microgram per liter. One can see here there's the characteristic absorption of the nitrate. The nitrate concentration would have a linear correlation with the absorption, and so one could perform or calculate some kind of it would be, how to say, it's possible to do quantitative analysis with nitrate in deionized water, but if we do not measure in deionized water but in real water samples, it looks different. We have here, for example, a real water sample from the Wiesecker, also from the 8th of March 22, that are spiked with nitrate, also between the 0.1 and 25 milligram per liter. We spiked the real water samples to simulate the increase of nitrate, while the measuring period and one can see the strong interference of the characteristic absorption and the absorption of the matrix. And here there's no, let's say, linear correlation between the nitrate and the absorption, so it is much more complicated to calculate the concentration of the nitrate. But one would need some kind of algorithm to differentiate between the matrix and absorption and to get access to the nitrate concentration. For that, the project partner A.U.G Signals in Canada put a lot of effort into calculating nitrate concentrations in surface water. They used up to 1,400 data sets of absorption spectra to perform calibrations and to determine the detection limit. They used some kind of deep learning regression algorithm to calculate the nitrate concentration and perform cross validations to show the results of these regression algorithms, and found out that the convolutional neural network with linear regression was the best one. The results are shown here graphically. Here on the x-axis we have the number of data sets up to 1,400 and a bit more. On the y-axis we have the concentration of the nitrate, and there are usually blue and red dots. The blue dots belong to the true value, which means that are the nitrate concentrations determined by some laboratory standard analytics, and the predicted values in red, they are calculated by these regression algorithms. And in the best case, like it is here in this area, the red and blue dots should overlap. That means that the calculated concentration match with the measured calculations. And with these results, they could calculate a detection limit for nitrate in surface water, which would be 0.025 milligram per liter. With that, we are already at the summary and outlook. So for the cloud-based data management system, let's say we need the sensors for the water analysis that are available. They should be suitable for the use in the field, robust, cost-effective, and need to bring high analytical quality. That would be for example, physical, chemical, or biosensors. With them, it is possible to monitor the needed parameters, for example, microorganism, nitrate, pesticides, drugs, pH, turbidity, and so on. Of course, the classical analytics is needed as a control instance to control the sensors and give more information, or in the first, some additional information to the cloud-based data system. We need this smart networking between the sensors and the classical analytics and some kind of metadata models or the databases. And with that, it is possible to do some process control impact-related analytics. And at the end, the sensors can be a key to efficient environmental monitoring to detect and control dynamic processes at an early stage. The networking of sensors and the intelligent evaluation of the data will lead to a shift in the environmental analysis. And the cloud-based data management system will be able to issue recommendations for an action independently and very quickly. Well, with that, I'm at the end. Well, I want to thank to my project partners, of course, to my working group, to especially Michael Seidel. And I think it took me 20 minutes. There's time for questions.
Yes, thank you very much for your talk.